Welcome back.
Now remember what our objective was. Our objective was to quantify the distance between a pair of distributions. Now this entropy sure will give us the average information contained in a particular distribution. Now how is this related to what our objective is? So let us define one other term. Okay, suppose Px and Qx are two distributions. Actually there is a slight abuse of notation here. See here this P was probability, the probability measure. Here this P is the mass function because we are looking at a discrete random variable. Okay, and yeah, so when I write P and Q are two distributions, I am talking about mass functions again. So we have to be careful about that. I mean now we are looking at discrete random variables because for for continuous random variables there is something called differential entropy which looks similar mathematically but interpretations are slightly different. But anyway, suppose P and Q are two distributions. So compute, let us say that we compute, let me just be clear about the definition. I will tell you why. This thing what I am writing is not symmetric. So suppose I look at the expectation of two distributions on the same sample space again, right? On the same sample space. This goes without saying. Let me go to the next page. Define expectation of negative of log of Qx. This expectation is computed with respect to Px. Okay. What does this give you? So negative of log of Q of x will give you the information or surprisal associated with the events under the distribution Q, correct? Right. Now if you take expectation with respect to Px, then what am I saying? I am saying that my actual samples have come from Px, but I am estimating Px to be Qx. Now if I do that, then what is the average surprisal that I get? If I consider that my true distribution is Qx, or rather if my true distribution is Px, while I consider that the samples are coming from Qx. Does it make sense? The other way to interpret this is that what is the average information that Qx contains with respect to Px or about Px. Suppose Px and Qx were the same, then what happens? This will become the entropy of Px. Now if Px and Qx are not same, they are two distributions, then this quantity is telling you what is the average information that one distribution contains about the other. See, suppose I take my Qx to be a Gaussian distribution with mean 3, right, and my Px is a Gaussian distribution with mean 0. While the samples are actually coming from a Gaussian distribution with mean 0, I am wrongly thinking that my samples are coming from distribution with mean 3, right. I compute surprisals for all samples and then take an average. What am I computing? I am computing what is the information that Q contains with respect to P, or rather what is the mistake that I am incurring by wrongly making an assumption that my reality is Q while it was P. Okay. So you can interpret it in multiple ways, and this has a name. Okay, this is actually written as H P comma Q. What is this called? This is called the cross entropy. Okay, and by definition, cross entropy is not symmetric. Do you see this? H of P comma Q is not equal to H of Q comma P by definition. Okay, you observe this. Now again, going back to our original objective, our objective was to define distance between distributions. Now consider again this notational misnomer will be there. Okay, so these are mass functions for no discrete random variables and mass functions. Okay, consider, take entropy of P and subtract it with the cross entropy between P and Q. This will be, let me just get the math right, Px log Px plus Px log Qx. Yeah, the reason I am staring at it is it's asymmetric, right? Because it is asymmetric, if I write it the other way, if I write H, Q and P, you will have a different expression altogether, but anyway, it does not matter. Okay. Now, what is this expression telling you? Let us interpret this, right. So, this will tell you the average information, the entropy of P is the average information in P, right. Cross entropy is the information that Q has about P. If I take the difference between those two, what am I looking at? I am saying what is the error that I have incurred by wrongly choosing Q over P, or wrongly choosing Q while it should have been P, or the extra bit of information that is there in Q and not in P. Make sense? What is the difference between the entropy and the cross entropy? It is telling you that if I look at the average information in P and the cross entropy, or the information that is in Q with respect to P, subtract them both, I will get the extra information that is there in Q which is not in P. Make sense? Right. So, now that is equal to, just use the definition of logarithms, just log correct, this is what it is. Now, suppose P and Q were the same, then what would this quantity be? It will be 0. Suppose P and Q are very far away from each other, what would this quantity be? It will be high. So, take two things as homework, show that this quantity is not symmetric. Okay. So, let me write this quantity as and by the way, this is what is called as the KL divergence, the Kullback-Leibler divergence between two distributions. So, this is what is to be shown is that to show that dKL of between P and Q is not the same as KL between Q and P, okay, and also show that this is non-negative, and show that this is equal to 0 if and only if P matches with Q. It is a two-side result. Okay. So, please take, I mean this is, use the definitions and use the law of logarithms and the definitions of density functions, you will get it. That is how you do it. Take it as a homework and do it. Now, we got our objective, right. We were looking at a measure that would tell us how far or close a pair of distributions are, and KL divergence is one such measure. And also you can show that this is not a metric, in the sense that this does not obey the law of triangularity. Why? It is obvious, right. If it is not symmetric, if a metric is not symmetric, then it cannot satisfy the law of triangularity. Okay, just show that. I mean, it's pretty simple to show. Oh, anyway, so this is not a metric in the sense, in the strictest mathematical sense. Okay, but it gives you a sense of the closeness between pair of distributions. It's called the KL divergence. Okay, so a similar definition exists for the case of continuous random variables, and as I said, we assume that most of our data is continuous, right, in most of the time. So I'll also give you a similar definition. So this is called, there's differential entropy and differential cross entropy, right, so which is X is the definition of KL divergence for continuous random variable cases. Looks very similar to the discrete case. The only thing is these are density functions now, okay, and cannot be interpreted as probabilities, but yeah, of course they are density functions, right. P and Q, the KL between P and Q, here it was between Q and P, so it's P log Q by P, here it is P log P by Q. Did I make a mistake? No, it's the same thing. See, this will stay the same. See, HP minus HQ minus P. Sorry, Q comma P. See, HP minus HQ comma P. See, only the cross entropy term changes. The entropy term does not change. So, if it's HQ comma P, what will happen? Q, right? Hold on, let me just confirm it once. P and Q is my bad. I think the mistake is that it is the difference. Okay, I'll just change it this way. The minimal changes. Difference between the cross entropy and entropy. Okay, so in this case, what happens? It is because of this asymmetry. There's always a question. Hold on. Hold on. Just give me a second. I'll correct this. See, cross entropy, this is P and Q, this is correct. So HP and Q is expectation this, yeah, this is, this will become, hold on, so HP is P log Px, so this is the cross entropy minus entropy. Okay, fine. I think there's a minus here and a plus here, right? And this will make it P by Q. Okay, correct. Yeah. Yes. This is the KL between P and Q. Correct. Thanks for that. Difference between the cross entropy and entropy. It's because of the asymmetry, right? So this algebra does not work out. Okay, thanks for that. So this is not asymmetric and so on. Yeah, so now the definition falls, right? So it's P log P by Q, correct. Okay. Any other questions here? No, this is not cross entropy. No, this is the difference between the cross entropy and entropy. HPQ is the cross entropy, Hp is the entropy. So we are looking at the difference between the cross entropy and entropy. No, test it out. Yeah, it should be the difference between cross entropy and entropy. So now this, I am also saying one other thing. I am also saying the cross entropy is always higher than entropy, no? Yeah, so that should be the case, because if these two match, it's always upper bounded by, or it is lower bounded by entropy, always. See, that's why you need to take the difference between, see, when I said difference, HP minus HPQ or HPQ minus HP, both of them are differences. But to ensure that it's non-negative, because by definition cross entropy is bounded by entropy, you will have to ensure that you take the higher and subtract the lower. That's all the definition. Okay, fine. So for the continuous random variable case, the KL divergence is defined this way. Okay, any other questions here? So you would have heard about this, no? To err is human. It's becoming more and more prominent these days. The more the mistakes that you do, the more it is proven that you are a human being and not an AI. Anyway, okay, yeah. So for distribution functions I use capital, for our mass and mass functions, for density functions I use small p and q. Okay. We will stop here and continue in the next lecture.